All right, day 6 notes. We're going to talk about some other things about functions that you guys have studied in the past that could be important, specifically symmetry. Now, there's lots of different kinds of symmetry. Generally, symmetry is where you fold something, you get the same shape, but it could be a little more interesting than that. Y-axis symmetry is if you fold something across the y-axis. So, as a specific example, maybe like a parabola gets folded across. Now, one of the interesting things that we might talk about is that it has the same value on either side, positive and negative x's. Also, if you're to integrate, this area would be 7, for instance, and this one would be 7. So there's symmetry left to right. Now what we call this, College Board and AP refer to this as even symmetry. And maybe the way to remember that is that even polynomials usually have even symmetry. So quadratics, quartics, things to even powers. Also, cosine has even symmetry. Anyways, a little more information about that. It's like, parabola is a really good generic even symmetry, y-axis symmetry kind of problem. And the basic idea is if you plug A in and you get B out for the coordinates, then if you plug negative A in, then you should also get B out. So if you plug negatives in, you get the same as positives, which also happens with cosine. X-axis symmetry would be like a circle, right? Where you could fold it across the x-axis and you get it. The only problem is that it's not a function. It fails the vertical line test. So we're probably not going to necessarily deal with them, talk about that idea much. So not something we're going to be working with right now. Y equals x symmetry, that would be across y equals x line, and in a circle has that. Probably mainly a circle. I mean, there are certain, there's other functions that could have that kind of symmetry, but we're not going to do that now. Okay, so you don't need to worry about it. We are definitely going to do y-axis symmetry. We call it even symmetry, and then the other one's called origin symmetry. And another name for it's called odd symmetry. And you might guess that like an odd function, like a cubic, you kind of think of as a polynomial with an odd power. So that's a good, I don't know, to me that makes it easier to remember that this is odd symmetry now. It's a double reflection. Okay, so it's like you take 1/2 and you fold it twice. So it could be over the y and over the x-axis. So you could take this half, fold it over here, and then fold it down here, and you get the other half. So it's two folds, and they call it symmetry about the origin. We call it odd. Now the characteristic is if you plug A in, you get B out. If you plug negative A in, you get negative B out. Now sine, y equals sine has this type of symmetry. But in general, cubics or things with odd polynomials with odd degrees can have this kind of symmetry. So, how do we determine if a function is even or odd? You might be tempted to be like, oh, well, this has an even power, so it's even. This one has odd power, so it's odd. It's not that simple. We could look at a sketch. We're going to come up with a better way in a second. And this is a parabola that's been shifted up 5 units. And yes, it does have symmetry across the y-axis. So it is even symmetry. You're like, I told you so. I told you. Well, let's try this one. This is a cubic that's been shifted up 5 units. So it kind of looks like this. It does not have symmetry about the origin anymore. It does not have even symmetry. It doesn't have odd symmetry. It doesn't have any kind of symmetry other than about this point, which doesn't have a special name. So we would say neither for this one, okay? It has, it has a symmetry, related to y equals 5, but not y equals 0. There's no special name for that. Now, you might be like, oh, it was odd, so it should be odd. Nope. If it didn't have the plus 5, it would. Now, you might be like, well, how do I figure this out? You can say, well, this is even, right? And this is odd. And even times an odd is an even. No, I don't know. I don't think I would rely on that. Okay. So these graphs are going to get harder to graph. I mean, sketching these graphs may be easy to determine, but that's not going to really be realistic. So, maybe one of you guys might say, "Oh, well, let's plug in a point," because I keep saying that these special relationships up here have to happen. So maybe if we test that out, so we're like, well, let's plug 2 and negative 2 in. If I plug 2 in, I get 2 squared times sine 2 is 4 sine 2. And you plug in negative 2 and you get sine of negative 2, which gives you positive 4. Now, sine of negative 2, sine does have this odd symmetry. So these are trig identities that we're going to go ahead and take to be true. And we talked about these last chapter. We said sine of negative theta equals negative sine theta. So a negative on the inside actually has the same effect as negative on the outside. That's for sine, but cosine just equals itself, whether you plug negative or positive in. So, and this actually comes from this idea that this has odd symmetry and this has even symmetry. So, sine of negative 2 is going to be negative sine of 2. And then you could compare these to each other and say, oh, well, they're the opposite. So that must mean, since these are opposite, that it's going to be, that's going to be odd. Okay. And that's a good idea. Now, is that enough to really prove the symmetry, to really, without a doubt, just because you picked a pair of points? We could have gotten lucky. Some functions, this could happen for some pair of points, but not all pair of points. So one pair of points is not enough. So we need to come up with a better, more thorough justification. Okay. So this is the way I want you to do on the homework. We're not going to do point check. We're going to do variable check. So we're going to try and make it more generic. So I'm going to say, let's plug a and negative a in. Okay. And so this little table is just a nice way to organize it. So a squared sine of a, right? Then you plug negative a in. Negative a squared sine of negative a. Now that's going to equal positive a sine of negative a. And then this is going to equal negative a sine of a. All right. Now here you could say, well, for any value of a, any pair of a and negative a, they're going to be the opposite, and therefore it has odd symmetry. So we'll accept that. Don't use a specific pair of numbers because that might be too narrow. Let's try and make it generic. So by the way, I think we were trying to predict that maybe this was even. No, it actually turned out to be odd. Even times an odd is an even, but that plan of attack doesn't work. So here's a couple more. This is the way you're going to do it on the homework. Okay, you can't just be like, oh well, this one's even, and this one's even, and this one's even, so the whole thing's even. No, that's not a good way to predict it. So, and this is a crazy graph. Like, you're not going to graph this. Okay, so you're not going to be able to picture it, visualize it. So we're going to make this little table. This is the kind of work I need to see and on your next test where you plug in a pair of x's, a positive and negative, but we're going to keep it generic and just call it a. So first step is just plug it in. Okay. And so, and you see this, it's pretty straightforward. Just plug it into both of them. So we're going to take a pretty, straightforward approach on all these. Now you got to say, okay, well, could I drop the absolute values here? Because isn't the absolute value of A just going to be A? Well, we don't know if A is negative or not. Just because you said this is positive A and negative A might be a negative number. So this might actually come out as a negative number, and this is a positive number. So we have to leave the absolute values there. And then A to the fourth is for sure A to the fourth. And cosine of A is cosine of A. Now here, we could say that the absolute value of negative A is A, right? If you take the absolute value of negative 5, isn't that the same as the absolute value of positive 5? So we can do that. Can't get rid of the absolute values, but we could get rid of the negative. And then negative A squared is going to be positive A to the fourth. Sorry, negative A to the fourth is going to be positive A to the fourth. And then what's the trig identity for cosine negative? That it equals the same thing as the positive. So now we've shown that these are equal to each other, that they are, the same, and therefore that is even symmetry. That's always going to be even symmetry. Okay? So this is the kind of work I want you to show. So next one, this is the one that we're just doing up there, but I'm going to show you how to do it without a graph. So I'm going to do A and negative A. And we're going to plug them into that function. And the table is just a nice way to organize your information, which is good to help someone feel confident in your answer. So we're going to plug A in, and we're going to plug negative A in. Now this is going to be A cubed plus 5. This is going to be negative A cubed plus 5. Now you might be like, oh, these are the opposite of each other. Nope. That would have to have a negative in front of the 5. And they're not equal to each other. And they're not opposite. So it's going to be neither, which is the conclusion we made when we looked at the graph. Okay? Some other interesting applications from this even odd symmetry. I talked about it up there that for an even function, the integral on the left and the right would be the same. For an even function, if you have a graph and you have the slope on one side, let's say it's 3, and the corresponding slope on the other side is going to be negative 3. They're not perpendicular, okay? All right, this is for an even function. The slopes at corresponding points are simply opposite, just negative, not negative reciprocal, just negative. For an odd function, if you're going to do an integral, find the area. First of all, the slopes on both sides are actually going to be equal to each other. They're going to have the same slopes. So the slopes at corresponding points, corresponding meaning they kind of match up to each other, are equal. They're the same. Now the integral, if you were to integrate this from a negative A to a positive A, the area is going to always end up being 0 because this negative and this positive, they have the same shape, same area, but this is negative, that's positive, you cancel each other out, you always get 0. So anyways, just some other interesting things. So on the back, we're going to talk about inverse functions, which we've been talking about a bit. And we talked about them quite a bit for logs and exponentials, but this is, any function can have an inverse function. So some basic ideas from last week that we were talking about is that if, I like to use logs and exponentials as just a good generic pair of inverse functions, okay? So this is really just, some function f of x. Now, one of the things is that you can flip it across y equals x, right? So this point ends up over here, and it kind of looks like this. Now that looks like a log graph just because I like this pair, but we're going to say it's the inverse of x, so superscript -1, That doesn't mean exponent. It doesn't mean to put it in the denominator. It means inverse. So you got to be, you got to understand the context of that superscript -1 to know if it means inverse. And usually you probably wouldn't put an exponent right there anyways. So the thing to watch out for is that y equals the inverse of x does not mean 1 over f of x. Okay, it does not mean that, right? Okay. But here are some interesting things. If you're to look at a pair of corresponding points, if you look at a point here and call this AB, well, this one's going to be BA because the x's and y's get switched. Okay? And it's a reflection across y equals x. Something else that's interesting is the slope. So if you draw the slope at one of these points and the slope of the corresponding point over here, if you did it just right, one interesting thing is they would always cross each other on y equals x. But, and I'll convince you that this makes sense in a second, if the slope here was 3/2, then the slope of the corresponding point over here would be 2/3. They're not, so the slopes are really just the upside down version of each other. They're just the reciprocal. They're not the negative reciprocal, they're just the reciprocal. Okay? They're not perpendicular. Okay? Okay? Just upside down. So I guess the way to summarize that is that f of -1x derivative prime equals 1 over f prime of x. That's the relationship between the slopes. Now, the reason that makes sense is because slope is rise over run, right? So you're saying, well, the slope of this is going to be change in y over change in x. But remember, x and y get changed. So now, what was the change in y is now the change in x. What was the change in x is now the change in y. The rise over run gets swapped and becomes, the rise ends up on the bottom, the run ends up on top. So you get the same slopes, but just upside down of each other. Totally makes sense. Okay? So that's some calculus stuff. Now, you're going to need to be able to find the equation of an inverse function, which is something that you should have done in previous, like at least algebra 2. The first step is to use this idea we keep talking about where you just switch the x's and y's. So, for instance, if this is our function, then we're going to say our inverse function is, you're going to put x's where the y is and y's where the x's are. So right there, this is your inverse function. Now, what we usually want to do to make it look nicer is to solve for the new y. You want to get this guy by itself, okay? And that's usually where it gets a little messy. It's not hard, high-level stuff. It's just messy. How do you get that y by itself? Now, in this case right here, I'd probably cross-multiply, and I would get xy plus 3x equals y minus 2. So if you're trying to solve for a variable and it's stuck in the denominator, you want to get out of the denominator. Now I'm trying to get this y by itself, but now the y's are popping up in multiple places. So we want to get the y's together on the same side and the non-y's on the other side. So it's kind of up to you. We could say, okay, well, let's subtract y from both sides and then subtract 3x from both sides. And so then we get -3x minus 2. Now, if you're trying to solve for something, you have multiple terms involving that thing you're trying to solve for, you want to combine them together as like terms, but the coefficients here are not like terms. So we need a trick. What we're going to do is we're going to factor the y out of both of those so that we can eventually get y by itself. And then we divide by x minus 1, whole thing. Okay? And so the new inverse function, f of x, is going to be y equals -3x minus 2 over x minus 1. Alternatively, you could factor a negative out of the top and bottom. You get 3x plus 2 over 1 minus x. But one of those would be your answer. So that's how. So cross multiplied, we isolate the y terms, right? And then we combine the y terms, and that's using a little trick by factoring the y out, and then we solve for y. Now, you should have done this in some class before, all right? But it's basic idea that you just swap the x's and y's, and then you just try and get the new y by itself. It gets a little messy sometimes in between. So we will be talking later on about how to deal with that. There are some calculus tricks for dealing with that, so you don't necessarily have to do all that. But for now, next test, you're gonna have some problems like this, and hopefully you just feel really confident about them. You're just careful. Now, some functions don't actually have inverse functions. Okay, for instance, a parabola, the whole thing does not have an inverse function. If you were to flip it across y equals x, you would get this. And it's not a function because it fails the vertical line test. It's an inverse relation. That's different than saying it's an inverse function. Now, one of the reasons that we say it doesn't, so what happens is usually we restrict it to just the left or the right, so you just get the top or the bottom, and so then it is a function. But the whole parabola altogether doesn't. Now, there's some terms for that. If a function is not one-to-one, 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 monogamous is sort of like just a funny way of trying to describe it. Now, functions in general, a function, the definition of function is that every input, which is an x value, every input has exactly one output, one y. Okay? Now, parabolas themselves are functions because every x has one y value out. Now, we get the same y values out for different x's, that's okay. But that's where this monogamous one-to-one idea comes from. That every x has exactly one y, but also every y has exactly one x. A parabola doesn't have that. If you pick this y equals 4, it's going to tell you that it goes with x equals 2 and x equals negative 2. It's like the y equals 4 is cheating with one x and the other x. And this is actually starting to sound like more and more relationships, such that x's and whatever. So it passes a vertical line test and it passes a horizontal line test at the same time. So for instance, a cubic is one-to-one because it passes a vertical line test and it passes a horizontal line test. And therefore, when you get its function, its inverse is also a function because the original curve had to be one-to-one for the inverse to be a function. Now, if there's an issue, like we said here, a lot of times we get around it by restricting it to only part of the function. Now, one of the other things in the warm-up I said we're going to talk about is what happens when you put an absolute value in the inside of a function. I don't know if any of you guys have seen this before. Now, we're going to start with this generic function. I'm going to add some numbers here just to make it a little easier to keep track of stuff. Okay? Now, I am going to give you problems like this in your next test where I give you generic function and I ask you to do some different things to it. Move it, flip it, absolute values, whatever. Now, you guys should like this because this is your parent function that you're not having to even come up with. You're just going to work with this. Now, here's the interesting thing. We could just play around with some values first just to kind of get a feeling for what happens. I don't want you to just believe me. I want you to make sense. If you plug -1 in, okay, so if we're going to do this function from this function, if you plug -1 in, it's going to be the same as f of 1, right? So that means when you plug, let's put some values on here. So when you plug -1 in, you actually get what's happening at +1. When you plug +1 in, you get what's happening at +1 also. So that means that +1 and -1 are going to have the same value. They're both going to have what the positive one value was originally. If you plug 0 in, of course, you're going to get 0 for both of them. If you plug in -2, you're going to get what's happening at +2. So at +2, you have the 0. So you get this one, and then you get this one. What you should start to see is that whenever we plug a negative in to an absolute value and it forces it to be positive, we're getting a mirror image of what's happening here. So at 3, we had this graph over here. Now, essentially, if you plug any positive ins, it looks just the same as it was before because that doesn't really do anything. But when you plug negatives in, you're getting what's happening over here on the positives. So this is what the graph looks like. What happens is it takes the right side and it flips it across the y-axis, and it gets rid of what was on the left side originally. It gets covered up. So you get rid of the left side and you replace it with a mirror image of the right side. So that's it, and hopefully it makes sense to you just by plugging some numbers in that you start to see that. So happening essentially, the original negative side just disappears and gets covered up by a mirror image of the right side. So that's what happens when absolute values are inside. When they're outside, they just flip everything that's negative in the y direction up in the y direction. But anything inside a function with the x affects it left or right. So that's it. You should try your assignment and check your answers and be ready to figure out what you got wrong with my help. Okay.